All right, so I've been talking about E being positive, E is spontaneous. We know if delta G is negative, that means spontaneous. So of course those things are related, and they're also going to be related to equilibrium constant, because we know if that's greater than 1, the reaction goes to the right. So because electrons flowing is work, we know that delta G, free energy, energy available to do work. We can put those together in the equation we have here, where work equals free energy, which is negative NFE. And we got a few new things in there. And the signs are different, right? Because delta G has to be negative to be spontaneous, E has to be positive to be spontaneous. So the N is going to be the moles of electrons. What that is when you balance a redox reaction, you know how you make the E's the same so you can cancel them out? That number that you're canceling, not adding together, but the number that you cancel out, that's the mole of electrons. So if you make them both equal to 6, you cancel out 6, that becomes a 6. The F is going to be Faraday's constant, which I think on your packet is just 96,500. I don't care which one you use. It's really 96,485. The C is a coulomb, so coulomb per mole of electron. That's a constant that gives you the amount of charge you get per mole of electrons. And then you multiply that by cell potential, and it really bothers me that that J is lowercase. It should really be uppercase. So joules per coulomb. So we've got cell potential is the energy we get per coulomb. Faraday's constant is the charge we get per mole of electrons. We multiply that by moles, and we get work in joules. So again, our answer's in joules. Make sure you're putting those units on there, et cetera, et cetera. I gave you an example problem to try. Before I do it for you, I'd like you to at least balance the reaction and calculate E, and then I'll kind of guide you on how to calculate K. All right, so hopefully you guys realize from the balance equation that we need to flip this guy right here. So I'll just flip him over. And I'll flip that E value. And then I'm going to need to multiply the reaction through by 2 to get the electrons to balance. Do I multiply the E by 2? No. No. You never multiply the E by coefficients. So it's not quite like Hess's law. It's a little bit different. And our E for this is 0.67 volts. Okay, so that's phase 1. You guys good so far? Yeah. You got that? No problem. All right, so now we want to find the equilibrium constant. What's the only equation we've learned so far that has equilibrium constant in it? Negative RT ln K. So we know that delta G equals negative RT ln K. We also just learned that delta G equals negative NFE. So now we can find equilibrium constant, right? We can set them equal to each other?
Yes.
All right, let's set them equal to each other. So what's R? 8.31 joules. What's T? 298. Where's the standard? ln K. What's N? 2, because that's the amount that we canceled. The amount of electrons we cancel out is the N. F is going to be 96,485. And the E is the 0.67 volts. So now we just have to solve for K. And hopefully you guys get something like that. Try it on your calculator just to be sure you can do it. And I will have rounded at the very end. All right. Part 2 of the lesson is going to be concentration cells. Now we're kind of going into non-standard cells. Remember, standard conditions are going to be your 25 Celsius, your 1 atm, but it's also 1 molar. So now we're going to change the molarity of the solutions. And there's a couple different ways you can make what's called a concentration cell. You can actually have one where you have the exact same thing on both sides, and the only difference is the concentration, and that will actually cause a difference in potential and a flow of electrons. And then we'll do an example where we have different electrodes like a normal cell, but the concentrations are different, and there's a new equation that kind of goes with all that. So we're going to draw it. I'm going to start my drawing here with my beakers, and they both have zinc in them. So I've got my 2 sticks of zinc. I got my wire. What am I missing right now? I'm missing my salt bridge. Gotta have the salt bridge, or else the electricity stops. And then in solution, I'm going to have Zn2 plus, Zn2 plus. Let's say that the left one is the 1.0 molar and the right one is the 2.0 molar. Which way are the electrons going to flow? From everything you know and common sense, which way do you think the electrons flow? To the left, from the higher to the lower. That's what you learn, like when you learn about osmosis and everything. It always goes from higher to lower. Keep in mind, though, that the concentrations represent the ions in solution. The cell is going to run until those concentrations become equal. And if you think about the 2 reactions we would have going on, oops. All right, we have zinc being reduced, and we also have zinc being oxidized. Which one causes us to make more ions? The reduction or the oxidation? The oxidation actually makes more ions. The side with the oxidation is going to be the side that increases in molarity, where the side with the reduction, because the ions are becoming pure zinc, is the one that reduces in molarity. So we want the higher molarity to go down and the lower molarity to go up. So instead of the electrons flowing from higher to lower, they actually flow from lower to higher. So it's not intuitive. They're actually going to go from the 1 molar to the 2 molar. So the anode is going to be the lower molarity, and the cathode is going to be the higher molarity. So again, it's not like osmosis where, you know, the ions go from a higher gradient to a lower gradient, or a higher molarity to a lower molarity. It's actually going to go from lower to higher because we want the electrons to be lost, and that forms more ions, increasing the molarity, and then where the electrons are gained, that decreases the molarity, and it will stop when those molarities are no longer different from each other. Now, if we continue going through this problem, the voltages for these, see, this one's the anode, this one's the cathode. The voltages are essentially the same. The anode voltage is negative 0.76, and the cathode voltage is positive 0.76. So technically, when we add these together, everything would cancel out, but if I keep it here, keeping in mind that the cathode is the 2 molar and the anode is the 1 molar ion, and I keep that all in there, I end up with Zn2 plus 2 molar plus pure zinc makes pure zinc, and Zn2 plus 1 molar with a standard E of 0, but it's no longer standard because we have these 2 different molarities. We actually have an equation that we use to put in these non-standard molarities. And it's another equation that I really like to say. You know, I like to say Henderson-Hasselbalch. This one's called Nernst. And we'll come back to the slide in just a moment. If it's not standard, we use the Nernst equation. We just Nernst it. All right, so again with the Nernst equation, it's really going to be RT over MF times ln Q, like that. And order of operations, you would do all of the multiplying and dividing first, and then subtract it from the standard E. The standard E from the chart. The Q equals K, it doesn't mean it is equilibrium constant, it just means you do the equilibrium constant expression with given concentrations. Now, the reason why I don't have a box around that one, I have it around 25 Celsius, is the one in the box in red is the one we usually use because it's usually at 25 Celsius. We use 8.31. Faraday's constant is constant, and so what was done is that they combined the R298, Faraday's constant, and like the natural number from the natural log, and we get this E minus, and again, it's going to be 0.0592. I think your book says 0.0591. They changed it when we changed books, and I sort of never changed it. I don't care which one you use. Times log of Q, so ln became log. And then I kind of give you a rearrangement down here. If the cell comes to 0 and is done, remember every time you calculate the voltage, that's the voltage before you start. What happens to a battery as you use it? Eventually, it doesn't work anymore. It runs out, you have to recharge it or get new ones. The same thing happens here. When the chemical reaction inside your battery comes to equilibrium, you're no longer getting any voltage, and you're at equilibrium. So if we set that E to 0 and we change the Q to a K, we now have a relationship between E and log K. And before we go back to our the problem we were just doing, if we go back a couple problems, this one right here, we can actually use that equation instead of doing these two equal to each other. These two equal to each other basically give you that Nernst relationship. So we could have just done log K equals NE over 0.0592, which would have been the 2 electrons, the 0.67 volts, 0.0592. And if you work it out, you get 4.3 times 10 to the 22nd. So you get a slightly different, we got 4.7, this one says 4.3. It's really the power is most important. So you could have used that equation instead of what we did. They're doing the same thing. The point is the same thing. So that's just that derivation of the Nernst. All right, so back to the concentration cell we were working on. We now need to use the Nernst equation. Your sign to use the Nernst equation is when the molarities are not 1. That's how you know. So we're going to do the Nernst equation for this, where we're going to do E equals, well, oops, that shouldn't be a standard E, sorry. E equals, our standard E is actually 0, and I will pull that down so you know. E equals 0, and then the rest of the Nernst equation is minus 0.0592 over N. What's N in this situation? 2. It was the 2 that we canceled out, times the log of Q. Well, Q is products over reactants, but what don't you include in Q? No solids, no liquids, right? These zincs right here are solids. You got to be really careful when you use the Nernst and you do Q with these equations, because some things are ions, some things are gases, some things are solids, some things are liquids. No solids or liquids. So I need to do my product zinc, which is 1.0 molar, over my reactant zinc, which is 2.0 molar. So it's still products over reactants, products on top, reactants on the bottom. It's still products over reactants, not including any solids. And we can work that out, and we get a really, really small voltage. Negative 0.0089. So we barely get any voltage. It's not a big difference. But if we use different molarities, like if it was a 1 to 4, or, the bigger the difference, the more of a change in the voltage we're going to get. Oh, that shouldn't be negative. Sorry, positive. 0